The mass in kilograms of a species of fish in the UK has population mean 4.2 and standard deviation 0.25. So that is the population as a whole. An environmentalist believes that the fish in a particular river are smaller on average than those in other rivers. A random sample of 100 fish of this species taken from the river has sample mean 4.16 kilograms. Stating a necessary assumption, test at the 5% significance level whether the environmentalist is correct. We'll get back to the assumption in a minute. When I first looked at it, I thought, where are we making the assumption? But let's just follow through the process and then I'll tell you. So H naught is going to be, this is going to be, by the way, a normal distribution hypothesis test. We've got the mean and standard deviation. So we're going to say that actually the mean is 4.2 in the river as well. That's our null hypothesis because we can do calculations using it. And H1 is that actually the mean is slightly less than that in the river. Now, of course, with the sample, it is less, but we have to show it's statistically significant because it could just happen through chance. We just happen to have picked lots of the smaller fish. It's just what are the chances of that actually happening? Okay, so some things are not on the mark scheme, but I think are good practice anyway. I'm going to assume H naught is true. It's only using that I can do calculations. Assume H naught is true. Um, And here's where the other assumption is going to be. So I'm assuming the mean is 4.2. I also have to assume the standard deviation in the fish in the river is the same as in the general population. Assume we tend to always, well, we always do that in this A-level maths. Um, but it is an assumption that you're making because it might not be true. They might have a different spread. They're, different fish. Okay, I'm now going to define my continuous random variable. Let x be the distribution of masses fish in a particular river. Now we'll get onto the sampling bit in a minute, but what we have is that x is going to follow a normal distribution with the same mean and the same standard deviation according, that is, to h naught. But we are taking a sample of 100 fish, which means we have a sampling distribution. And this is then going to follow a slightly different normal distribution. It could be 4.2, but you do 0.25 squared divided by n, so divided by 100. The good news is that this is actually given in the formula book at the, well, sorry, in the formula at the start of the paper. Here it is. So it's not like actually something you have to get to grasp like really strongly. You can just like learn and use it. And I got to say, when I did over maths, I don't think maybe my teacher showed me, but I don't think I ever fully understood it. It was only when I came back to teach it, I was like, oh, okay, now I get it. So I'm gonna just very quickly explain like why we are dividing by 100 because we have our original distribution x, but then we're taking 100 values from it. So we might get some that are, on the like at the upper end and at the lower end, fine. But lots of them are going to be where the probability is much higher. It's just going to happen. We're going to be picking these points probably. And then for this sample mean distribution, after we've got our 100 points, we are finding the mean of it. So you're very unlikely to get a mean over here because there's going to be loads of values to the left. And so what you actually get is it's going to have the same value as the mean of the original distribution because you can imagine it's going to be symmetrical once you take lots of values, but it's going to just be much taller here. You're not going to get many values around here because you're taking 100 values of the mass and then finding the mean. What are the chances it's going to be really, really low? So you just get this compressed distribution, which is why we divide without, I haven't proven it or anything. There's deeper maths going on here for where this really comes from. But we divide the variance by 100. And thus we actually get a new standard deviation. Sometimes it's called the standard error. I'm not going to do that here. So our standard deviation for our sample is then going to be 0.25 divided by 10. Okay, I'm not going to go into more detail on that, but it's just worth like thinking about and just read up on it more if you're interested. I would advise that. So we've actually got from our um, sample mean as 4.16. So it is below the actual what we expect the mean to be, the 4.2. So we're going to work out the chance of that happening. What's the probability that the sample mean is actually less than 4.16? That value and below. So we're working out this area here. And that's what your calculator's doing when you use the, what is it, distribution, normal CD. The lower value is just going to be very, very small. I don't know, you put in whatever you like, just a big negative number. And then the upper one is going to be 4.16. This sigma is going to be 0.25 divided by 10. Must use that. And the mean is our original, like H0 mean, 4.2. Gives us 0.0547. And that is less than 5%, which I haven't actually talked about, but that was what we were told at the start, to do a 5% significance level. So two ways to think about this. One way is to say, right, the critical region is at 5%, and so that would be our like critical value. Maybe you call it X critical or something. And our 4.16 is actually above it, so it's not in the critical region, and therefore we're not going to reject H0. By the way, you get away with saying accept H0, but technically speaking, that there's just not enough evidence to reject it. It doesn't mean we're saying it's definitely true. So technically it is do not reject H0. The other way to think about it, instead of like talking about the critical region, is to say, right, we're finding the chance of this happening. So if the chance was say like 30% of it happening, if it's getting a sample mean of 4.16, that's pretty good. That's actually reasonably likely. So when it's probably true that actually the sample mean was 4.2 and we just happened to have got a lower, sorry, the population was 4.2 and the sample mean was just a little bit lower, because there's a good chance of it happening. If the probability was say 0.1%, then we'd be saying that, well, there's not much chance of that happening, given that the mean was 4.2. So actually, it's probably that our original assumption wasn't true, and that's why you reject it when it's lower than the significance level, but actually do not reject it if it's above. And I know it's very close, but we're saying there's a 5.47 chance of it happening, just due to luck, due to chance. That is above our threshold, our cutoff for what we're going to allow, and that's why we're not rejecting H0. So two different explanations there. And then finally, we just need to give some context. Insufficient, you either say sufficient or insufficient, in this case, evidence at the 5% level. And that's just something we have to decide. What is our threshold going to be for acceptance or rejecting, or not rejecting? At the 5% level, that that the fish, I'm actually reading off some paper now, but look back at the original question for this bit. So they believe that the fish are smaller on average than those. So we're basically going to use this to help us. That the fish in the particular river are smaller on average in other rivers. Nicely done. A lot of marks here. You've got to be hitting these key points, the H0, H1, the assumption. Do not forget that. Okay, that's where I think the examiner's report say lots of people didn't realize that we're making that assumption in our sample, in our actual river population. We're saying it is going to be the same as the whole population average. Yeah, normal distribution, sampling distribution, hit all those things, get the probability, compare it with the significance level, do not reject or reject, depending on it. Gives inclusion context. Just practice this. It's because it's actually one that, it's one in the stats paper that it's a lot of marks, but if you practice it enough, you get into the swing of it, then, it's not as bad as like an unseen question. We're going to find others later in the paper that are like, well, I've never seen this before, that can be a lot easier to trip us up. So well done.